Hi everyone, welcome to our exploration of science versus pseudoscience. In this video, we'll uncover what sets true science apart from claims that sound scientific but lack evidence. So let's get started. Science is the systematic study of the natural world through observation and experimentation. It follows a structured approach known as the scientific method. This method involves forming hypotheses, conducting experiments, and drawing conclusions based on reproducible evidence. For example, scientists may observe a natural phenomenon, like plant growth, form a hypothesis about what affects it, and then test that hypothesis in controlled conditions. But what about pseudoscience? Pseudoscience refers to beliefs or practices that are presented as scientific but don't follow the scientific method. Pseudoscience often lacks proper testing and relies on anecdotal evidence or personal testimonies rather than empirical data. For instance, a claim that this crystal can cure all ailments is not supported by rigorous scientific testing. Now, let's dive into the key differences between science and pseudoscience. First, let's talk about testing and evidence. If someone claims a crystal can heal all illnesses, what's the first thing you should ask them? Is it A, how much does it cost? B, can I try it right now? Or C, is there any specific evidence that supports this? Obviously, the correct answer is C. Is there any scientific evidence that supports this? To illustrate the importance of scientific backing, let's look at a clip that highlights the differences in evidence types.
Defining science is surprisingly tricky. There's a common idea that all science should, in some form or another, be related to testing against empirical evidence. But some scientific activities are primarily theoretical, and different disciplines approach empiricism with varying goals, methodologies, and standards. 20th century philosopher Karl Popper tried to solve the demarcation problem with a simple rule. He argued that in order for a theory to be scientific, it must be falsifiable or able to be proven wrong.
Claims without specific backing often use personal stories or testimonials. However, as explained here, science demands controlled, repeatable evidence to support any theory. Next, we have falsifiability. In science, a theory can be proven if new evidence contradicts it. Pseudoscience, however, often makes claims that cannot be tested or proven wrong. Why is it important for scientists to share their findings with others before making a claim public? A, to get feedback and ensure their results are accurate. B, to show off their work. Or C, to compete with other scientists. The correct answer is A, to get feedback and ensure their results are accurate. As we just discussed, the ability to test claims is crucial. Now, let's see how this concept is illustrated in the next clip.
Cherry picking. A time range can be carefully chosen to exclude the impact of a major event right outside it. And picking specific data points can hide important changes in between. Even when there's nothing wrong with the graph itself, leaving out relevant data can give a misleading impression. This chart of how many people watch the Super Bowl each year makes it look like the event's popularity is exploding. But it's not accounting for population growth. The ratings have actually held steady because while the number of football fans has increased, their share of overall viewership has not.
As shown here, for any scientific theory to hold, it must be capable of being proven wrong. This is where pseudoscience fails, offering claims that are conventionally immune to refutation. Finally, let's discuss peer review. Science relies on the peer review process where findings are shared with other experts for validation. Pseudoscience often lacks this rigorous review process, making it easy for misinformation to spread. Which of these is a sign that a claim might be pseudoscience? A, the claim can be tested and proven wrong. B, the claim relies on personal stories instead of scientific evidence, or C, the claim is backed by multiple experiments. The correct answer is B, the claim relies on personal stories instead of scientific evidence. Now, let's play a quick game called Fact or Fiction. I'll present some statements and you decide whether they are based on science or pseudoscience. Statement 1. Vaccines cause autism. Statement 2. The earth revolves around the sun. Statement 3. Homeopathic medicine can cure cancer. The correct answers are the following. For statement 1, pseudoscience. For statement 2, science. And for statement 3, pseudoscience. Next, we have a scenario for our second game. Test it. Imagine someone claims that a new diet pill will make you lose weight instantly. How would you test this claim? A. Ask people who've used it for their opinions. B. Run an experiment with a control group and measure results over time. Or C. Take the pill yourself and see what happens. In this scenario, the correct approach is B. Run an experiment with a control group and measure results over time. This method ensures scientific rigor. In conclusion, understanding the differences between science and pseudoscience is critical for making informed decisions. Believing in pseudoscience can lead to dangerous consequences, like rejecting vaccines or using ineffective treatments. The next time you hear a bold claim, remember to ask, does it follow the scientific method or could it be pseudoscience? Thanks for watching, guys. Stay curious and keep questioning the world around you.